Thank you very much, Mike. So today, the title of my talk is Problematizing a Scientific Practice, examining how resources are recruited to problematize scientific activity. And in full disclosure, this is dissertation work that I conducted back before I came to LSRI, and is right now in the midst of a revise and resubmit. So I was excited to bring this here. It turns out that you can't just turn your dissertation into papers and just get them out the door. You have to sit on them, and then you get revisions, and you get all this feedback, and you have to tweak it. So that's where this is coming from. So this is data that I collected back in 2010 to 2011 in my work with some middle school teachers. So I'm excited to be bringing this forward to you, and then also in talking with you a little bit about some of these key arguments. And so I'm going to begin with this focus on problems. Problems are central to inquiry and learning, and Dewey has talked about them way back when as problems stimulating reflective inquiry. So getting students and learners really to think about perplexity, confusion, or doubt, and that's the root of a lot of the meaningful learning that goes on. And problems are central features of some of these seminal educational interventions that we've talked about in the late 90s as well as the early 2000s, from cognitive apprenticeship to problem-based learning to fostering a community of learners. They also happen to all have acronyms. But what's common among all sort of these approaches is that they talk about problems as an important driver of meaningful engagement, so that by engaging in this problem-solving process, learners are more equipped to think about authentic problems. Okay? But today I'm going to be talking about the work of problematizing as a process. So what does it mean to problematize? Oftentimes problems can't just be introduced or given. They have to be identified and then pursued. So some of the key folks who have been talking about problematizing, Hebert and Reiser and Engel, they talk about problematizing as a process of defining and working on the problem. And these are not just arbitrary problems. These problems leave an important sort of residue, or as Hebert calls it, mathematically fertile, right? They're central to the discipline. Reiser talks about problematizing as an approach to guide the learner into facing complexity in the domain. So thinking about disciplinary problems as not stripping away and making more simple the things that we bring into the classroom, but rather maintaining that complexity and then preparing students, scaffolding students into wading through it. Engel and Conant, in their work, talk about problematizing as an individual or collective action that encourages disciplinary uncertainties that are then taken up by the students. So in thinking about this notion of problematizing, there's a couple key things that I want to point out. One is sort of a dispositional, motivational aspect that when you problematize something, you generate a need to actually resolve something. You commit attention to it and interest and investment in the problem. And in turn, you're actually putting the onus on the student to actually take ownership over their learning, both what they learn and how they learn it. But secondly, there's this epistemic component, that problems are not just poof out of thin air. They're rooted in actually how knowledge and knowing is defined in the discipline. And so fostering productive disciplinary uncertainty reflects sort of the work that science or math experts actually grapple with in their daily work. And so how is this problematizing reflected in the work of science? Well, we know from a lot of the documentation of how scientists work that science knowledge in itself is by nature sort of uncertain and emergent. It's constantly changing. And Kirsch talks about the fact that there's always gaps. There's persistent gaps in models, and existing explanatory models are always somehow flawed. And so it's this pursuit of identifying where those gaps are and trying to resolve them to make them more coherent and incomplete. Carey and Smith talk about this as sort of an epistemic view of knowledge as being problematic. Science knowledge is always an approximation of what we know to be true. And then finally, Latour and Wooger, in some of their documentation of the dialogue that happens amongst scientists, noted that even though knowledge is in fact rooted in evidence, it's highly negotiated and contested. And there's this entire process of actually moving from data all the way to claims and calling them facts. And that process is not easy. It's constantly being negotiated. And so we see that problematizing is actually rooted and closely tied with sort of the epistemic processes of generating science knowledge, as well as the knowledge itself that is being contested constantly and revised over time. And so for the purposes of this talk, I'm going to be drawing on Engel's conceptualization of problematizing as the individual or collective action that encourages disciplinary uncertainty. And I'm going to be talking about problematizing as the identification of those uncertainties, whether they're inconsistencies, incongruity, or incoherence, that then in turn drives the creation or revision or refinement of scientific knowledge. Let's take a closer look at what problematizing actually looks like in practice. So in full disclosure, I am not a particle physicist. I don't know if anyone is here. And if you are, you can correct everything that I'm presenting here on this slide. But Pickering back in 1995 wrote an entire sort of ethnography of how particle physics go about doing their work. And one of those pieces is his documentation of Morpurgo and his colleagues and the construction of a tool called the Magnetic Levitation Electrometer, or the MLE. What's important to note here is that the MLE was designed to look for fractionally charged particles and during lab experiments, and that at that time, sort of particle physics in the 1960s, what was accepted was that electrical charge was thought to always be quantized, right? And so he's working here sort of on this hypothesis that there are, in fact, the existence of these like free and partially charged particles called quarks. And so in Pickering's documentation of this entire process, he noted his path to constructing this piece of machinery was not simple or straightforward. So what does that mean? And so in constructing this machinery here, these are sort of photos of a photograph of what that machine looked like, and then also sort of the setup of where the magnet is and where the electrical charges were thought to be passed, etc. In designing that piece of equipment, he was drawing on a lot of rich conceptual understanding, including sort of existing electrostatic theory at that time, and he was using that to actually to put the instrument together. And he hypothesized that given what we know, this is how we ought to design that instrument. But furthermore, he was drawing on this hypothesis that if in fact these isolated charged particles existed, this is one way that we could try to capture it. And of course, if we just follow a simple sort of scientific method, if it yielded the right data, and then that data would actually then feed back to whether or not our hypothesis was supported or not supported. And of course, we know that this is not how science happens. It turns out that the data that they got was totally unexpected, and then that they had to go back and do several rounds of tweaking both the machinery as well as their conceptual understanding of what is actually happening, what's underlying this machinery. And so this back and forth is what Pickering called sort of the mangle, that the scientists were constantly moving back and forth between what's on the left-hand side, which is what he called material activity, so the design of the instruments, the collection of the data, and then their conceptual understanding, some of which were really well accepted, considered principles in physics, some of which were really emergent and new and sort of subject to change. And that they were constantly moving back and forth in this space, and that's where problematizing is actually occurring, because it involves this process of considering what's happening right now in our lab, the material activity, and considering it in light of the things that I think I know about what's going on in the world, as well as the taken for granted knowledge that we've established as a field. And that it's this back and forth process that then leads to the identification of these important disciplinary gaps, inconsistencies, incoherence, etc., that then drives our process forward. Okay? And it turns out right now, especially in the United States, given the NGSS framework as well as the NRC framework, there's actually a real opportunity to try to bring this way of engaging in science in the classroom. And I think this NRC figure is particularly helpful because it describes what's happening sort of in the real world in the investigation on the left-hand side, which we could think about as the material activity of what happens in the classroom, the tweaking, the collection of data, etc. And then it talks about it in relation to theories, models, and hypotheses, which is sort of the conceptual understanding underlying that material activity. And this work of arguing, critiquing, and analyzing that happens in the middle, the practice itself, presumes that there's some identified gap. There's something that actually needs to be addressed. That's all underlying it. I'm not going to argue with somebody if we already agree upon some sort of claim or explanation. But the practices presume that there's something that needs to be figured out. And I'm going to be thinking about, in this talk, how that actually happens, how that surfaces for students in middle school classrooms. So how can we support the work of problematizing? Well, there's a couple things that are sort of key to learning environments that may be able to seed opportunities for students to engage in this work. One is this idea of introducing phenomenon or real-world scenarios or problems, or driving questions that can motivate students into inquiry into these disciplinary issues. Another is trying to think about getting students to construct the representations, models, etc., is what Christina Schwartz is focused on, but that these models then reflect sort of key conceptual ideas in the discipline. We could also present sort of intentionally competing arguments or models in the classroom to encourage students in thinking about how you vet them and how you evaluate those claims. And then you can also foster norms that encourage students to propose alternatives, engage in interpretation, and justify their reasoning. And I want to point out that some of these can be seeded as features of curriculum materials. But we also know that curriculum, anytime you see a curriculum being enacted in the classroom, there's a great deal of variation in what we see actually happening. And part of that is rooted in the fact that curriculum enactment is rooted in social interaction and engagement. It involves teachers and students, some of whom bring unexpected things to the lesson that you've so carefully designed. It's embedded in a local context, and teachers actually have to do a lot of work to try to tweak and adapt and meet the needs of their local environment and their students. And so in turn, even though these resources can be seeded as features of curriculum materials, how these resources are taken up and actually used to engage in the work of problematizing can vary greatly. So in this talk, I'm going to be focusing on trying to describe what this looks like in one teacher's classroom. So given that problematizing is about the search for disciplinary uncertainty, and it involves this recruitment of material activity with conceptual ideas and considering them in light of each other, how do teachers and students actually draw on these resources to engage in the work of problematizing? The curriculum context is a middle school 6th through 8th grade curriculum called Investigating and Questioning Our World Through Science and Technology. And there's a lot of schools in the Chicagoland area who have adopted these set of materials. And there are a couple features of the materials that I want to point out that make it a rich context for thinking about how problematizing happens. So one, every unit, and you'll see two here, one on the left is the first 6th grade physics unit, and then on the right is the intro to chemistry unit. Each one is grounded in a driving question. So for the physics unit, it's about how can I believe my eyes? So it's about the role of light in seeing and how light interacts with different types of matter. The second one is the chemistry unit, which the driving question is, how can I smell something from a distance? So it's about the particulate nature of matter, matter moving amongst different phases, and how we can capture sort of the interactions there that actually result in me being able to smell something that's cooking in the oven down the hall. Furthermore, inside the unit are various investigations throughout that actually get students to generate empirical and observational data. And then there are discussions embedded in the materials to try to get students to make sense of those data and data patterns. And then finally, there's an explicit emphasis on the practices. So getting students to generate explanations, models, and arguments, and then actually refine them over time as they get more and more data. So having their understanding evolve as they encounter more and more complex phenomenon. So these features, I think, lend itself to understanding how students grapple with this new phenomenon and new data, and whether or not they're thinking about how they all kind of fit together. So as part of a larger study, I selected 3 lessons in the unit, 2 in the physics unit and 1 in the chemistry unit, and I observed them between October and February over a school year. The larger study involved 4 6th grade teachers, so I watched them do these identical lessons in their classrooms. Each of these lessons were multiple days, and I chose these lessons because within those multiple days, students see a demonstration of a new phenomenon they hadn't encountered before. They involve students in collecting data and making observations. They encourage students in making sense of what it is that they see, and then actually drawing on their knowledge to actually make sense of what they've observed, to actually explain what they know. So these lessons sort of help me identify kind of these small moments where all of these things are sort of coming together. And so it's a rich opportunity to think about whether or not students are actually revising and reconsidering their ideas over time. The case study classroom I'm going to be focusing on is one of Miss B. She's been teaching for about 20 years and actually using the iQuest materials in some way, shape, or form for about 5 years. She also teaches 2 classes of mathematics and uses a reformed mathematics curriculum. So she's used to engaging students in talk as a way of constructing knowledge, both in science as well as in math. She teaches at a public K-8 school in the Midwest, where there is a relatively diverse population of students, and she teaches all of the 6th grade science classes in that school, and there's approximately 25 students per class. As a part of the data collection, I watched and observed teachers enacting each of these lessons, and then I generated transcripts both from the video as well as the field notes. And then every time I was in the classroom, I conducted pre and post interviews with the teachers to get a sense of what their goals were, what they had changed or adapted, and then to reflect with them on how the lesson went and whether or not they got where they wanted students to go. And then afterwards, because it involved 4 teachers enacting the same lessons, I generated these memos to try to figure out what were the variations between how teachers were doing this. Did the teachers differentially support sense-making during whole group discussions? What explicit connections were being made between that lesson and the previous ideas that they worked on or the goals of the unit? So the memos are really used to kind of capture some of these variations. And it's through that process that I identified Ms. B as a good candidate for these case studies because she was constantly engaged in this work of connecting what they know with what they were doing. So the first thing I did was I tried to categorize, I went through the transcript line by line to try to categorize the resources that students and teachers were bringing to bear during these sense-making discussions. So I reviewed transcripts from all 4 classrooms across the 3 lessons, and then I used a thematic analysis to identify sort of categories. And then I went back to the actual curriculum materials and the interviews with the teachers, as well as sort of thinking about what got displayed inside each classroom. And that resulted in 3 categories of resources. And so here we have data and activities, co-constructed ideas, and then students' lived experiences. So what are those 3 types of resources? So the data from the investigation is sort of the material stuff. This is the curriculum embedded activities, phenomenon, or demonstrations, or the data that's generated out of them. And these were things that they were working on during an existing lesson or from previous lessons, but they're sort of empirical in nature. On the right, co-constructed ideas, these are ideas that are claims. These have a conceptual sense to them. It's not just about, did you get X, Y, and Z from the data? It's, how does that then inform our understanding of how light behaves or how particles behave? So these are conceptual ideas that are co-constructed through discussions. Oftentimes, they were displayed in the classroom or on the whiteboards as posters, and then the students and teachers referred to them explicitly as models, principles, or explanations. And these were ideas that were generated over the course of multiple lessons. So oftentimes any given claim or model or principle, the students could cite multiple pieces of evidence for how they actually know that. And then lastly, as we always know, students bring in a variety of experiences from their home or community or with family and friends that they actually bring into the classroom to make sense of what they see. So these are things that were outside of the scope of what was introduced in the curriculum. And you can see across here that there's some material stuff that they were working with, and then conceptual understandings. And so I really wanted to see how those things interacted in the talk. Then, after identifying the resources, I defined episodes. And so I looked at the transcript and I segmented them to episodes based on shifts in either the type of resources that were being recruited, so if there was a change in one of the 3 things that they were drawing on, or how they were being used to actually support the sense making, if they were moving from construction to evaluation or critique. So that comprised of a single episode. And the episode could consist of multiple talk turns from multiple speakers. So you can imagine that multiple students might be drawing on the same resource to generate a claim, for example. And so that talk would be would consist of one single episode. But if they then turn to using a model or an explanation to sort of evaluate those claims, that would be segmented as the start of the next episode. So I did some data reduction here, and I only focused on the episodes where one of the 3 resources were explicitly mentioned by the teachers or students, which is about 50% across the 3 lessons for Ms. B, and that number didn't vary too much across the 4 teachers who were participating in the study. So then I went back to my key question about problematizing. So how does their use of resources then inform the work of problematizing? I looked at clusters of episodes where multiple resources were at play to give an indication that they were actually considering the material stuff that they were doing in light of their conceptual understanding. And I defined a cluster as 2 or more consecutive episodes where different resources were being used. Then I identified 5 of these clusters for Miss B across the 3 lessons that were observed. And then within the talk that comprised of the episodes in that cluster, I looked at 4 things. I looked for what gap was identified, if any, how and whom the resources were recruited by and to identify the gap, what was made uncertain or contentious about what they were doing, and then what productive work is being accomplished by identifying that gap. And this is really based on my conceptualization of problematizing. Yeah, Susan?
Just a clarifying question. What if was the gap the same in these clusters?
No.
Okay.
And I'm going to present 2 cases. Well, maybe you can see for yourself if you think they're the similar type of gap. But no, the gaps were not similar. And so there's actually 3 cases that I highlight in sort of the written version of this talk. But today I'm going to have time to talk in depth about 2 of these cases. They both come from the physics unit about light and its behavior. In the first case, they're trying to investigate how does light know how to do that? And then in the second case, they're trying to figure out what happened to those missing colors of light. So in the first case, just as a reminder, the driving question for the unit is, can I believe my eyes? It's about light and its behavior and how it affects how I see. So over the first 5 lessons in this unit, the student developed this model that they had put up and they had drawn a picture of that stated that light comes from a source, travels in a straight line through an unblocked path, bounces off an object, and hits my eyes. Okay? And so the visual representation was some form of this. So you have the eye, kind of looks like an eye, over on the bottom right here. You have a light source which is emitting light rays in all directions, but some of which is directed at the eye, which is how I can see it. And when it hits an object, it bounces off, it travels in a straight path, bounces off, and enters my eye. And that's what allows me to see it. Right? But the teacher in this classroom introduces an interesting phenomenon. She takes a flashlight, which is a source of light, and she shines it at 2 different types of objects. One of which, this one is a brick wall, but she shines it at a piece of paper, and then she shines it at a mirror. And the students immediately begin to observe some differences here in the way that light is behaving. So remember, the model up to this point is that light bounces off objects and comes and enters my eye. But now they've detected a discrepancy here in how light behaves with one object and the other object. And so the question in this lesson is, what does that mean for my model that I'm seeing these different ways of bouncing off objects? So when Miss B actually shines the flashlight, she turns off all the lights and covers all the windows in the room. When she shines the flashlight on a piece of paper taped to the whiteboard, this is not problematic for any of the students. They immediately say, well, it's because we see that piece of paper on the wall because the light is bouncing off the paper and going into my eyes, right? Their model can be readily recruited to explain the thing that they're seeing. But then when she shines the flashlight on a mirror, they begin to notice that light was actually behaving differently. So here's a portion of the transcript. And so Jaden earlier said, well, the light is hitting the paper and bouncing off and going into your eye. But she says, but now what if I use a mirror? Okay, and she aims that same flashlight at a handheld mirror. And she sometimes aims it actually directly at some of the students. And some of them are like, oh, what are you doing? And she says, well, this is kind of fun. How long is class? How long can I do this for? And then she says, okay, is the light hitting? And she says, when I did the paper, you weren't yelling. And she aims it right back at the paper. And one of the male students says, because it's bouncing off differently. Now that may not seem like a really significant observation that the light can do different things with different objects, but this actually begins a conversation about what we mean by bouncing differently. So Alex begins proposing these explanations for why he thinks it's behaving differently. He says, I was going to say that you could see the flashlight on a mirror is brighter because that's what glass is made out of. So he's making a conjecture about how the substance, the stuff that the glass is made out of, might have something to do with why light is behaving differently now than it was before. But Miss B pushes on this. She says, but how does light know how to do that? How does light know to act differently when it hits this and react differently when it hits this, right? So she's not saying that he's wrong, but she says, how does light know to behave differently when it interacts with something that's made out of glass? Then Jorge comes in and he says, well, the mirror is like made, like you can see yourself when you flash light at it, and it just reflects. And then she continues to push. She says, what makes a mirror do that and not a piece of paper? And Jorge said, well, the mirror is made to do that. The paper is made, there's this idea of substances being created to interact in particular ways, okay? So they're recruiting a lot of rich ideas to make sense of the demonstration, but the way that Ms. B interacts and responds to this gives them a sense that they're not quite yet at the level of explanation of trying to account for this interaction. She says, okay, a couple more ideas and we're going to try to figure out, should we collect some data, try to collect some more information about this to figure this out? Okay, so it's an open question still. She's accepting these candidate ideas, but there's this still a sense of that we can't really quite fully explain what we're seeing. So how do we make sense of this in thinking about sort of the material and conceptual things that they're bringing to the table? So one, we know that the students already have at the forefront of their mind this working model. And when they see this discrepant event, light bouncing off a mirror and not off of a piece of paper or a wall, they actually are drawing on these things to try to make sense of why is this happening, right? But an insufficiency emerges. So our current knowledge doesn't actually account for these differences in how light behaves. And Jorge and Alex both have a lot of rich ideas about how the substance may have something to do with what they're seeing, but they're not yet at the level of describing how light interacts with these substances and why it results in the way that it does. This actually then motivates them to go back and use a little light meter and actually describe more carefully the ways in which light is bouncing off a mirror and a piece of paper. And so you'll see here a flashlight, and at the end they attach a mirror and then a piece of paper, and then they try to follow the pathway of light using multiple trials to then try to figure out how is light bouncing off of those two things. Then they go back and revise their conceptual understanding. After collecting this empirical data, they figured out that light actually bounces in this very predictive sort of V-shaped way off of a mirror. But then with paper, across all of the data in the different groups, it was going in all sorts of different directions. So they were beginning to make sense of how light's interaction with these two different types of substances was resulting in them being able to maybe see and reflect off of a mirror and not do that with a piece of paper or a brick wall. So they're adding and deepening their understanding of how the substances or the materials, or in this case, the surface of the object, might influence light and its behavior as it's interacting with different types of matter. In the second case here, they're actually in that same physics unit, but a couple lessons later, and you'll see that their working model has improved and been refined over time. So instead of just talking about light bouncing off of an object, now they've got these multiple ways, okay? One of which is reflecting or scattering off, transmitting through, or getting absorbed by the object. So they've done a number of investigations where they looked at how light travels through opaque or transparent objects. They've taken measurements, for example, of what happens when you leave a flashlight on, shining on some water, what happens to the temperature, as indication or evidence that the energy from the light is actually being absorbed and doing some work. Okay? But now at this point, they've only been talking about white light. And so the issue at hand for this particular lesson is how this model can actually be used to account for colors of light and components of white light. And we know from doing some work with prisms and looking at rainbows that white light, even though it looks white, is actually comprised of the entire rainbow of colors, right? And so they're trying to figure out whether or not this model can actually help explain what happens when we're thinking about color, light, and components of white light. So again, the lesson begins with a demonstration, a little bit more complex one here. So the teacher turns off all the lights, covers all the windows, turns everything off except for this overhead projector. This overhead projector has a piece of black paper on it with a tiny slit sort of cut out of the middle. And the teacher does two things. She overlays a piece of C-Spectra paper, and then later, about halfway up, an orange filter. Okay? And so C-Spectra paper acts similar to a prism and sort of refracts that light. So what might you expect when she puts the C-Spectra paper on? What might you see on that whiteboard?
Colors.
Yeah, colors. Which colors? all the colors, right? And so that's what they see. So you'll see in the middle here that that's the light that transmits directly through the slit. But then on the two sides is what Laura's saying is the refracted colors. Those are the things that composed of the white light that got split when it entered through the C-spectra paper. So what's puzzling now is when the teacher places that orange filter on top of that overhead about halfway. And what the students observe is that in those portions where she's placed that orange filter, some of those components of light have disappeared. If you look really closely, you can see that the blue and the purple, the violet, sort of on that right end of the spectrum, has now disappeared when they put that orange filter on. So again, there's this discrepancy. There's this puzzling phenomenon. What happened to those missing colors? They were originally there, but now that I put the orange filter on top of it, where did those missing colors go? And so that's the question that sort of drives this lesson. So one of the things to note is that when students look at this phenomenon, they've already experienced work with mixing different colors. So they've already done on a simulation the mixture of red and orange, red and yellow and green light to figure out what happens when those colors are combined. And so they readily bring those understandings into trying to make sense of what happens here. So Ms. B first says, what happened to those missing colors? I didn't do any magic, so it must be a phenomenon that we can actually explain. And then Lucy is a key player here in trying to figure out what's going on. And she draws on her understanding of color, mixing colors, to actually make sense. She says, you don't need the blue to make orange. So she's looking back here at this orange light and saying, well, orange light, I know that orange light is just the combination of red and yellow light. You don't need blue, and that's why it's not showing up. But Ms. B critiques in this way. She first acknowledges, she says, you're right, we don't need it. She concedes, she said, you're absolutely right. However, you didn't answer my question. And so she goes back to the overhead and she says, here's the white light, it disappeared. Where did it go? It was here. And she stands next to the overhead projector and she says, you're looking at me over here. And then she traces the path of light from the projector onto sort of the overhead glass and onto the whiteboard, and she says, here's the white light. Do you agree that it's coming up here? Do you all agree that it gets to here? And she's motioning the filter, right? And the students say, yeah. And so she says, so where does it go? So what she's pointing out about Lucy's idea is that it's not that she's wrong. Orange light is not composed of blue light, but she's saying it's insufficient for thinking about what is actually going on in this particular case. So for the phenomenon that we're trying to explain, the blue light was there, but now it's disappeared. So we have to figure out where it goes. Okay? So they continue after this to really focusing on the role of the filter and what it might be doing. And so one student proposes that the filter might be reflecting those colors. And so remember, reflection is one of those ways of describing how light bounces from their initial explanatory model. And some of the students say, I don't know, and Ms. B keeps pushing. She says, it's reflecting which colors, Lucy? She says blue, but she says, does anybody see blue? Right now, what Ms. B is doing is she's trying to get students to think about whether or not there's observational evidence for the claim that Lucy is proposing, which is the light is being reflected. And then the students say, no, I don't see it. I see orange in the background. And Ms. B says, if it was going to reflect blue, would you see blue? And the student says, yes. Somebody else says, I don't know. And she says, we could still go with what Colleen said, right? Like it gets there, but we don't know where. It's going somewhere. So in these turns of talk, there's a lot of things that are going on here. So one, there's a student who's proposing this idea of reflection. But then two, there's an evaluation of whether or not they have some evidence, some observational evidence, rooted in their prior activities of thinking about what's evidence that light is reflecting. We've got to be able to see it. So if we can't see it anywhere in the room, we can't account for this claim right now using what we have right now as available evidence. So if we again look at this idea of sort of the material and the conceptual sort of coming together, we see first Lucy was drawing on this idea of color mixture to try to figure out, she thinks that it's because the blue is actually not comprised of the orange. That's why it's happening. But there's some inconsistency here because this claim actually does not address the thing that they're trying to figure out. That blue light was originally there, but somehow we've got to account for where it's going. Later on, the multiple turns later, Lucy's drawing on this language of reflection, and she says, maybe it's being reflected. But then they go back and consider their prior investigations, and they realize that there's no evidentiary support for that model because with their observations, they don't see blue light being reflected anywhere in the room. And so identifying sort of these insufficiencies and inconsistencies actually gets them to eliminate a subset of the claims that they're proposing, and then later on test some new ones in light of existing available evidence. So again, we see the students kind of navigating their observations of the phenomenon and also bringing in some of their understanding of prior investigations alongside sort of these understandings about light and its behavior to try to figure out whether or not their claims are valid given the available evidence. Talking a lot faster than I thought. So just in terms of discussion and implications, so if we think about these two cases, what are the disciplinary gaps that emerge? In the first case, there's an insufficiency both for our current understanding of how light behaves, as well as our existing model to account for the thing that we're seeing. Even though we've talked about light bouncing off, we haven't yet accounted for the different ways that it does that. In the second case, there's this discrepancy between claims and available evidence, that I'm proposing something, but I don't actually yet have evidence to bolster or support those particular claims. And then I'm calling them disciplinary gaps because then it leads the students actually to go on to actually doing more investigation or generating more claims. And for each case, these gaps emerge out of considering the material and conceptual resources in light of each other. And what's important to note is that in the larger study of the 4 teachers, the teachers didn't differ significantly in how often they were drawing on these resources during the whole group discussion, but they did differ in whether or not they were actually considering them in light of each other. So teachers often talked about models and recruiting them and getting students, but they didn't think about how one problematized the other, which is the important work here of problematizing.
Can I just ask a clarifying question? So when you say what are the disciplinary gaps, why could you just remind us why are they disciplinary? What do you mean by disciplinary gaps as just opposed to gaps in understanding?
Yeah, so disciplinary gaps, when I was talking about problematizing in the beginning, disciplinary uncertainties that then have some sort of implication for building conceptual understanding. So in this case, because in both cases they're trying to co-construct an understanding of light, I guess I'm calling them disciplinary because in the first case, detecting that discrepancy leads them to the work of revising their conceptual model of how light works.
So it's not just any gap, like a gap could just be somebody doesn't understand what we're talking about.
That's right.
It's the gap that would lead you to the inquiry process that would lead to a better understanding.
Yeah, that's right.
The gaps that matter, kind of.
Yeah.
Thanks.
Yeah. Sonia, did you have a question?
Yeah, so I was thinking about what Lucy said about mixing colors, and I didn't see that as a conceptual gap between what light is made of, but a conceptual gap between how pigments work and how visible spectra light is split into 7 colors.
Yeah.
Right? Because she says like blue, like she says something like
You don't
purple
need
doesn't
blue,
need,
yeah.
which is comes from the understanding of pigment mixing, right? And I didn't see the teacher pick that out, which is very common for students to think about mixing colors and thinking
That's
how
right.
visible
That's
spectrum
right.
is going to.
That's right. And actually later on in the transcript that I don't present, they do tackle that issue because it continues to come up, this idea of color mixing versus light mixing, which they've already done in one round with the simulations, but it's a difficult thing to try to unpack why they behave differently and whether or not you can actually readily recruit that understanding of how colors are mixed to actually explain light. But yeah, that's something that comes up constantly all the time with this particular lesson. I think because it's foregrounded because they just did the simulation and they have ample experience with mixing different colors. How do you disentangle those and figure out what you can recruit, what's appropriate, what has an explanatory power when you're trying to think about this phenomenon?
The teacher jumps on that. The way the teacher said, she said, but you didn't answer my question, right? So
Yeah.
she doesn't say all that,
Yeah.
but she says, that may be that you don't need blue.
Yeah.
But you did, so I don't know, it feels like she's pointing to that's not the gap we're looking at, or I don't know what you do with that, but it's
Yeah.
very interesting.
Yeah. So there's a lot of work that she does, in my other observations of her classroom where she, I think maybe as a function of her experience with this particular curriculum, she kind of knows the kinds of things that are going to be, that students are going to bring to the table. And she has a sense of sort of this conceptual space of what are all the things that they're going to bring in, and then how do I sort of shepherd them in that space towards revising their model. And I think it's that level of expertise that maybe allows her to say, okay, you're absolutely right, but that's not what we're talking about here. Remember, this is what's happening. You've got white light that's got blue and purple, and all of a sudden it's gone. It's no longer on the whiteboard. What's going on here? Yeah, Laura.
Well, and she did use a piece of what the student said, because she used if you don't need blue, you're saying we don't need blue, where is the blue? Because we had it. So she
Whether we need it or not. we took it.
Right.
Yeah.
Yeah, so
Something
she
happened
built
to
off of
whether or
it.
not we
Where'd it
think
go?
we needed it or
Right.
not. Yeah, and I think it's that sort of sense of, especially because I saw the same lesson in 4 different classrooms, I was able to see that some teachers were able to sort of detect it and tackle it and figure out how to maneuver those ideas in a way that didn't necessarily say it's completely irrelevant here, but in a way that sort of centers the students on thinking about what does this mean for our developing explanation for this phenomenon right here. And I think that's expertise that's developed over time as you engage students constantly in conversation and you try to figure out how do I get them towards this very clear goal of refining their model while accepting all of the ideas that they're bringing to the fore. Any other clarification questions? Okay, just have a couple more slides. And so the other thing I wanted to point out is that the problematizing is actually happening at different steps in the scientific activity. So in the first case, it was sort of at the opening of the lesson where they were trying to motivate why they needed to actually explore and interrogate the model to begin with, right? We've already said that light bounces, it's bouncing off these objects. There's nothing that leads me to believe that it needs refinement. But the problematizing work that happens when she introduces this discrepancy is that they have to actually go back and reevaluate it. In the second case, they're actually engaged in the work of constructing candidate claims, and they're trying to figure out which of these candidate claims is sufficient or explanatory for the thing that I'm trying to figure out. So problematizing is not something that happens sort of in the beginning when you seed sort of and shape sort of the arc of inquiry, but constantly something that happens when you're trying to figure out how does this fit with that? Do they actually fit together? Can I develop a coherent story for what's actually going on, for the sort of mechanisms that are underlying light, or the way that particles travel, for example. And so there's a couple things that I want to discuss with you all. So sort of thinking about the implications of capturing this type of activity in the classroom. So one is thinking about how to help teachers develop a new lens for analyzing and creating curriculum materials. So Betsy Davis and other folks talk about curriculum being educative or sort of teacher-facing, trying to support students and support teachers in thinking about how to introduce the best representation or how to anticipate student misconceptions and thinking about how to teach particularly rich ideas in the discipline. But I think what the study highlights here is that not only do teachers need to know that about particular representations, ideas, they also need to be able to see curriculum sort of at the other level of each subsequent lesson offers opportunities for students to actually revise their ideas. So how do we tune them into those gaps? How do we introduce a lesson and say, how does this actually fit with sort of the story that students are creating in their heads about what light does? How do we get students to see that they're actually making incremental progress when they go from lesson to lesson, and they're not just jumping around from activity to activity, which can be very overwhelming if you think about a curriculum like iQuest. There's discussions, there's data, there's patterns, there's tables. How do you think about that sort of at this high view where it's really about the integration and incremental refinement of ideas over time? So I think there's opportunities there for thinking about how to support teachers in making sense of curriculum materials. And then second, how do we scaffold students into seeing and responding to these gaps? So you'll notice that in the 2 examples that I led, there was a lot of heavy lifting from Ms. B. She was the one who was doing the critique. She was the one that was highlighting discrepancy. But we want students to be actually being able to do the work, right? To actually take on these practices of disciplinary experts. And there's a lot of literature in both math and science teacher education that talks about emphasis on teachers noticing and responding to student thinking. But what this study makes me also think about is whether or not we can think about seeing and responding as a co-constructed activity, not as something that just the teacher is doing because it's a great pedagogical move, but how do we get students to actually take ownership of actually detecting some of those important things that gets them to say, yeah, but why is that? But didn't we say that it's like this, but this doesn't actually quite fit? So that discrepancy, the identification of discrepancy and meaningful gaps doesn't always have to come on the part of the teacher who's trying to actually carve out this space for them to work on, but rather it's the students who've taken this on almost as a disposition and a way of thinking about scientific knowledge. So I ended a couple minutes early, but I'm just curious about what you all think of these cases with respect to problematizing. Also because of the audience here, thinking about sort of disciplinary distinctions between how I portrayed this work in science versus in other disciplines in history or in literature, for example. But that's what I have for you today.